Hey, this video is going to cover topic 3.5, which is an introduction to experimental design. Our learning objectives are to identify the components of an experiment, describe elements of well-designed experiments, and then compare the different types of designs and methods. All right, so let's start with a very basic experiment. Now, experimental design has its roots in agriculture, so I'm going to use an example from agriculture. Okay. All right, so let's suppose that we have 12 young tomato seedlings, young plants, and what we're going to do is we're going to number them, place those numbers in a hat or a bowl, mix it up, and then assign those plants to two different groups. And then each group is going to be given a different treatment. We're going to be looking at the effect of fertilizer. So the first group is going to receive fertilizer, and the second group will not be receiving anything. And then after some time, weeks or months, then we're going to come back and we're going to look at the yield, right? Or maybe like the weight of the tomatoes that are produced by our two groups of plants. Okay. Right, so this is kind of the general basic flow of an experiment. We begin with our experimental units, which are the 12 plants. In the case of human studies, we call them subjects. But since we're just dealing with plants here, we'll call them the experimental units. Okay. There's some explanatory variable or factor. In this case, fertilizer is the variable, and there's two factors. You receive it or you don't. Okay. There's a response variable, which is an outcome that's measured at the end. This would be the weight or the yield of tomatoes. And then we also need to consider, like, there might be other things happening that we did not originally plan for, such as, maybe when we, designed this experiment, maybe in the greenhouse, we placed the fertilized plants on like an east-facing side and the unfertilized plants on a west-facing side. So unbeknownst to us at the beginning of the experiment, now maybe those fertilized plants got more sun than the unfertilized plants. Okay, and so now there's this dilemma, right? Say those are the plants that had heavier tomatoes, right? Is it because they were fertilized, or is it because they had more sun? Right now, there's two possible explanations for why that group of plants may have had the heavier tomatoes. Okay. So now we would call sun, it's called the confounding variable. It was not part of the original plan, but we recognized later, like, hey, it was a factor that may have affected the results. Right, so these are, again, just some terminology that we're going to use as we talk about experiments. All right, so this is a very basic experiment that has just one explanatory variable, which is, again, called a factor with just two levels. Let me show you a more complex experiment. This one is a two-factor experiment with, again, fertilizer at two levels, and then we have water as a second factor that has three levels. Okay, so with two levels of one factor and three levels of another factor, that gives us a total of 6 different combinations or treatments. Okay, so now those original 12 plants would get randomly assigned to 6 separate groups of 2 plants each. Okay, and the first group of plants would receive fertilizer and heavy watering. The second group would receive fertilizer and regular watering. The third group would receive fertilizer but no water. And then you see the other combinations there. Okay. So this is called a multi-factor experiment. All right, so let's go back, let's return to the basic one and talk about some of the elements of good design. Okay. So the first of which is comparison. Okay. In order to know whether fertilizer is increasing the fruit yield or decreasing it, we need to compare it to something. We need to have a baseline to compare it to. Okay, so having at least 2 treatments, or at least 2 treatment groups, is a necessity. All right, the second element of well-designed experiments is to have random assignment. Okay, this means using some sort of chance process to create our groups. Okay, we don't want any bias to creep into our experiment. So that's why we're going to leave it up to chance to decide which plants get assigned to which group. Okay. The third element is replication, which means having more than one experimental unit in each group. The reason we need replication is because we want to be able to measure the variability within each group, right? And that variability is going to help us see whether the differences in the outcome are significant or not. Okay? So the more replication you have, the better you're able to measure that variability. And then the fourth element is control. Okay? Now, our real purpose is to study the effect of fertilizer, but we know that there are other things that may affect fruit yield, right? And so we want to try to control those things and keep them constant for all the plants. So that would be in this basic experiment, watering them at the same level, providing them the same amount of sunlight. If pesticides are used, making sure that it's being used evenly on all the plants, right? Just trying to keep everything the same so that the only difference between our two groups of plants is the fertilizer, right? We're trying to isolate this as the only real difference between the plants. Right. Now, there are some things we can control and other things we can't control, right? Like the 12 original plants, right? They're not all going to be the exact same height and weight to begin with. Okay, there's going to be minute differences between them, and we can't control for that. So to help with the uncontrollable factors, we're going to let random assignment take care of that. Okay, so this is really important to know on the AP exam. Random assignment is going to help us balance out the effects of uncontrolled variables, right? So things like the height and weight of these original 12 plants, we can't control them. So random assignment should hopefully balance them out in these two groups, right? It would be very unlikely that all the tall plants get assigned to one group and all the short plants get assigned to the other group, right? Random assignment should balance out the height between the groups and the weight between the groups. Okay. All right. So now we need to turn our attention to experiments that deal with human subjects. And one concept that's important in medical studies is this idea of blinding. Now, I know these diagrams have blindfolds on the people, but it's just for visual purpose. We don't actually use blindfolds when we blind subjects. So blinding refers to keeping our subjects unaware of what treatment they're receiving. Okay. So these two subjects, right? One is going to receive the test pills, and the other is going to receive control pills. Okay. And they're not going to know which one they're receiving. Okay. Now, why would we want to do that? Well, again, it's to eliminate bias from creeping into our experiment, right? We don't want the subject's knowledge to in any way affect their outcome or their result. Now, double blind is when the subjects, right, are unaware of which treatment they're receiving, but also the doctor or the other people, the team working on the experiment don't know either. And the reason for that is because sometimes there's a doctor or a nurse or somebody who has to evaluate the patients, right? And we don't want that evaluation to be biased if the doctor knows, oh, this patient received the control pills and this patient received the test pills, right? That might influence the doctor's evaluation, which, could be a subjective thing, right? So we want to make sure that our doctor is giving the most objective, fair and unbiased evaluations. And in order to do that, we shouldn't let the doctor know which patient received which treatment. Okay. So again, single blind is when one party is unaware, and that's usually the patients or the subjects. Double blind is when both parties are unaware, so both the subjects and the evaluators or doctors. All right, so I mentioned placebo. And so a placebo is basically a treatment that has inactive ingredients, right? And for pills, it's just a sugar pill. Okay? And the placebo is going to look and taste just like the actual drug so that our patients can't tell the difference. Okay. So why do we need to use placebos in experiments? Well, so there's this thing called the placebo effect, right? which basically just says that if you give a patient a placebo, they still may show a response to it, right? It's a psychological response, right? The brain knows that it's receiving something, right? It doesn't know whether it's real or fake, but that could lead to your body releasing endorphins and other chemicals that might actually help you feel better or heal you. Okay. So we need to use placebos because we need to know how large that effect is. Okay. Because the drug has to show a stronger effect than the placebo effect, right? In order for us to conclude that it's effective, right? A drug might show an effect, but it might be the same sort of effect you get from a placebo. And that sort of drug is not really something that pharmaceutical companies want to bring to market. They want to bring to market drugs that can show stronger effects than the placebo effect. Okay. So again, we use placebos to kind of form a baseline, right? What sort of response would we expect when just using a placebo? And then we use the results of the drug to see whether it's stronger than the placebo effect, or maybe it's about equal to the placebo effect. Okay, so now let's talk about some more sophisticated designs. So at the very beginning, we showed a basic design where you have experimental units, you randomly assign them to groups, the groups receive different treatments, and then you compare at the end. Now, sometimes you may know ahead of time that the treatment might behave differently in different groups of subjects. Right? So for instance, maybe they're testing vaccines for COVID, and maybe they suspect that the vaccine may behave differently in males versus females. Well, if they have that suspicion, then they really should separate the subjects before they begin the experiment. Okay? In other words, they should just run 2 smaller scale experiments, right? Test the vaccine on a group of males, and then test the vaccine and a control, of course, on a group of females, right? And then you can measure the vaccine's effect on these 2 subgroups. So by separating our subjects, we're going to be able to see the effect of the vaccine or treatment better, and it will allow us for multiple comparisons, right? Maybe the vaccine works twice as better than the placebo in males, but in females, maybe the vaccine doesn't work as well. All right, so we can have 2 separate conclusions because we've run 2 smaller scale experiments. Something that I want to point out here is that one mistake that I've noticed that students make in the past is they always want to draw arrows here, making some final overall comparison, which I don't recommend that you do. I don't think it's necessary. I think it's better to just leave the diagram this way with the 2 separate comparisons in the end. Also, it's important that if you're ever asked to draw one of these diagrams on the AP exam, that you don't do the random assignment until after you've split your subjects into blocks. Okay, so the random assignment does not happen over here. Right here, the researcher, separates the subjects based on some criteria. In this case, it's gender. Right, so there's no randomization there. Right, all the males are in one block, all the females are in another block. Randomization only happens prior to assigning the treatments. Okay, so being male and being female, those aren't the treatments. Okay, the vaccine and the placebo, that would be the treatments. Randomization happens before that. And then this is our last design. It's called the match pairs design. And there's 2 different ways this can happen. So one is where you pair up groups of subjects. Okay, and one subject gets the treatment and the other subject gets a control. And then you compare the results just within that pair. Okay. This is analogous to twin studies, right? So you have a bunch of identical twins, right? And one person in each twin gets the treatment and one of the twins gets the control, and then you compare. Okay. Now, the reason why twin studies are popular sometimes is because when you have identical twins, right, that eliminates a lot of confounding variables because they are identical in for a lot of different factors. And so it really helps to reduce the variability that we see in the results. All right, so you can see here in this diagram that it's not always the first subject that gets the treatment. You see in the second pair here, the arrows crisscross, just showing that randomization has occurred, and this time the second subject is the one that gets the treatment and the first one is the one that gets the control. Okay. So matched pairs is like blocking, except each block contains only 2 individuals. Okay. And those individuals are as similar as possible. So, if you can do a twin study, that's great. Of course, twins are hard to find and hard to recruit into studies, so that's why they're not as common, but that would be kind of the ideal matched pairs design. But you don't have to have twins. You can just find 2 subjects that are similar to each other, right? Similar height, similar weight, similar age, smoking status, health status, right? You find all these criteria to match people up. Now, a different type of matched pair design is one where you have, instead of 2 subjects, you just have a single subject. And that subject is going to receive both the treatment and the control in a randomized order. Okay. So this is pretty common with like taste tests, right? You can do like, oh, I want to do a taste test and see, do people prefer Coke or do they prefer Pepsi? So I'm going to recruit a bunch of subjects. I'm going to give them 2 unlabeled cups. One contains Pepsi, one contains Coke. And then I'll flip a coin to decide which cup they drink first, and then they're going to tell me their preference, right? That would be one of these like matched pairs designs. Okay, so each subject is their own block. Each subject receives both the treatment and the control. The order will be randomized based on a coin flip or any other chance device. And then you compare the results of just that one subject. All right, so that is the end of this presentation. Thank you guys for watching.